In chapter 14, we're going to learn about ideals and factor rings. And ideals and factor rings are the equivalent of normal subgroups and factor groups that we studied in previous chapters. So let's revisit this idea of what a normal subgroup is and what we needed for a factor group to be able to define a factor group. So let's look at example 1. So when we had a normal subgroup N of a group G, then we were able to define a factor group using the operation of cosets, between cosets. So we had two cosets, Gn and Hn, and we said that Gn times Hn was defined as G times Hn. So we just had to multiply these representatives of our cosets together to get the result of this multiplication of cosets. Now, what we'd like to discuss now is how does this work with rings? So if we have a ring R and we have a subring A, then what kind of conditions do we have to put on the subring A so that we can talk about a factor ring R mod A? And this comes down to asking ourselves, what has to be true about A so that the coset operations of addition and multiplication that we see here make sense? So what has to be true about A so that it makes sense that A plus A, R plus A plus S plus A is equal to R plus S plus A? And similarly with multiplication. So what has to be true about A so that R plus A times S plus A is equal to R times S plus A? Okay, so let's look at addition first. And this operation actually makes perfect sense because all we really would need for this to make sense is that A is a normal subgroup of R under addition, so as an additive group. But we have that, we get that for free because R is abelian under addition. Our ring is abelian under addition. So if you look at a subring under addition, it already behaves. It is a normal subgroup under addition. So the coset addition makes sense just because of what's true about subring anyway. So let me write this down. So because R is abelian under addition. And so what we already know about coset addition for groups just carries through here. So what about multiplication though? And this is going to be a very, very informal discussion. So what if we take R plus A and multiply by S plus A? What, we have a coset, we multiply by another coset, what does it look like? Well, this is like R times S plus A times S plus R times A plus A squared if I just kind of distribute. And so think taking an element in R plus A and multiplying by an element in S plus A, and these are kind of the pieces that you get. You get R times S and then plus something in A times S plus R times something in A plus something in A times something in A. So that's what you would get. And so let's look at these pieces. A squared right here, it's something in A and times something in A. So you could think of this as, this is a set of all products of things in A times other things in A. But A is closed under multiplication, so if you take something in A and multiply it by something in A, you again have something in A. So that's really just A. So we can say, and I put equal in quotes here, that this is like RS plus AS plus RA plus just A, because we're not getting anything new. We're also not losing anything, but yeah, you have to take my word for that. Now, what do we want? So what we want this multiplication to result in R times S plus A. And so really what we want is that AS is equal to A and RA is also equal to A. Because if that's the case, then we could say we get our RS and then AS is just A and RA is just A, and then we have our A again. But if we're having something in A plus something in A plus something in A, closed under addition, we again just keep A. So this is equal in quotes RS plus A. And so we found what we'd like to be true. We would like A times S to just be A, and we want R times A just to be A. This is not automatically true. Remember that S and R are just elements in our ring. And so if we are saying AS is equal to A, it means you're taking something in A, you're multiplying by an S, you're getting something in A. So A times S is an element in A, and R times A is an element in A. So this is kind of like if you take an element in A and you multiply by something that's just in the ring, it kind of gets sucked into A. So you're taking something in A and it sucks things in. And we call this the absorption property. So this is the absorption property. That's what we would like our subring A to have, this property, in addition to just being a subring. And any subring that has this property gets a new name. We are going to call it an ideal. And that's our definition right here. So a subring A of a ring R is called a two-sided ideal of R if for every R in the ring and every A in A, both RA and AR are in A. So that is this absorption property. And if you want a picture, so here we have our ring R. In it, we have our subring A. And so we have an element A over here and we have an element R over here. And if they get multiplied together, they get sucked into A. So anything that touches something in A gets sucked into A. The result. Okay. So this is what we need to be able to talk about factor groups. But before we go there, we need to talk a little bit more about ideals and get a little bit better of an idea of what these new things, these new subrings that we call ideals, how they behave.